The original Data Encryption Standard, or DES, relied on a 56-bit key. As computational hardware advanced, the ability to simply brute force that key space moved from purely theoretical to practical. Security researchers definitively demonstrated that exhaustive key search attacks could crack a DES encrypted message in a matter of days by systematically testing every possible combination. This created an immediate crisis for the industry. Before a modern replacement like the Advanced Encryption Standard was developed, organizations had massive legacy infrastructures that required an instant, backwards-compatible security patch. The intuitive fix was straightforward. Instead of designing a completely new cryptographic architecture from scratch, network engineers decided to process their data through the exact same DES algorithm multiple times. When legacy systems face sudden obsolescence, it is a common operational mistake to assume that repeating a weak algorithm simply compounds its mathematical strength. This diagram outlines the double DES architecture. Plaintext P enters the first block and is encrypted by K1 to produce an intermediate ciphertext X. Value X is immediately routed into the second block, where K2 encrypts it again to produce the final ciphertext C. Because each stage requires a 56-bit key, adding the second stage appears to create a combined key length of 112 bits. The baseline assumption is that an attacker would need to perform 2 to the 112th power operations to break the cipher. However, this simple architecture contains a hidden vulnerability. The presence of that intermediate value X between the stages allows for a specific type of mathematical reduction. In theory, this double-layer approach should be impenetrable. But as we're about to see, linear chaining introduces a structural predictability that cryptanalysts can use to break the cipher in a fraction of the expected time. Cryptanalysts exploit this structure using a meet-in-the-middle attack. The absolute requirement for this method is that the attacker already possesses at least one known pair of plaintext and its exact resulting ciphertext. Looking back at the double DES flowchart, the target is X. The attacker isolates the midpoint linking the two encryption stages to divide and conquer the pipeline. In the forward phase of the attack, the known plaintext is encrypted using every single possible 56-bit variation of key 1. The resulting intermediate values are stored in a massive dataset and sorted. During the backward phase, the attacker takes the known ciphertext and runs it backward through a decryption algorithm. They test every possible variation of key 2 to generate a second set of potential intermediate values. The algorithm searches the two tables for a collision. If an intermediate value from the forward pass matches one from the backward pass, a valid pair for key 1 and key 2 has been identified. This process reduces the brute force complexity from 2 to the 112th down to approximately 2 to the 56th plus 2 to the 56th. That total workload evaluates to just 2 to the 57th power, a calculation easily handled by modern hardware. Exposing a discrete mathematical midpoint within the encryption chain neutralizes the added security of the second key, exposing the entire architecture to reduction attacks. To defeat these simple intermediate matches while still using the DES algorithm, the industry moved to triple DES, extending the pipeline to 3 stages. Data passes through an initial encryption using key 1, followed by a decryption stage using key 2, and finally a second encryption stage using key 3. That middle decryption step provides critical backwards compatibility. If a system administrator sets key 1 and key 2 to be identical, the first 2 stages mathematically cancel each other out, allowing the system to communicate perfectly with older, single DES legacy hardware. While triple DES is highly robust, secure applications like PGP and SMIME mandate the 3-key variant, ensuring all 3 stages use independent keys to maximize the cryptographic distance between the plaintext and the ciphertext. This technical diagram details the tables required for a theoretical known plaintext attack against triple DES. Adding a third stage increases complexity, but does not render the cipher perfectly invulnerable. By analyzing the specific intermediate values, labeled here as little a and big B sub j, within the 3-stage chain, cryptanalysts can still execute advanced table matching strategies to force key reductions. Triple DES functioned as a necessary patch to secure aging infrastructure. But its structural complexity and the high computational cost of running data through 3 passes highlighted the necessity for native, single-stage algorithms like AES. DES and AES are block ciphers. They mandate that all input data be perfectly aligned into fixed-size mathematical chunks, strictly enforcing a length of exactly 64 or 128 bits before processing can begin. This slide shows how to handle real-world messages that do not divide perfectly by the block size. The final, incomplete block of data requires message padding. To fill the empty space, a standard format will inject null values, followed by a specific byte count. This numeric count explicitly tells the decryption algorithm exactly how much of the block is actual data and how much is just filler. Cryptographic security requires strict data preparation. Formatting the plain text into perfect blocks is a necessary precondition, occurring long before the actual encryption math is executed. Once the data is sized into perfectly padded blocks, the system must dictate how those blocks interact over the course of a long file. The NIST Special Publication 800-38A defines 5 specific modes of operation for this exact purpose. This excerpt explains electronic codebook, or ECB mode, where each block is encoded independently using the exact same key. The flaw here is that identical blocks of input data will produce identical blocks of ciphertext, leaving the underlying structure and patterns completely visible. To effectively mask those data patterns, cipher block chaining, or CBC, operates as the standard mode for long transmissions. CBC creates a mandatory feedback loop. The finished ciphertext from the first block is routed back and combined with the raw plaintext of the second block using an XOR operation. Every block's final output mathematically depends on the block that preceded it. For systems that cannot wait for full blocks and require stream-oriented processing, cipher feedback mode translates these block mechanics to operate on a continuous bit-by-bit stream. Real-world security is the product of structural orchestration, the specific intersection of robust ciphers, rigorous padding, and interactive blockchaining modes.